Section 1. The Birth of a Dangerous Idea, from Fission to the Manhattan Project. The Manhattan Project did not arise overnight. It was the culmination of decades of scientific inquiry, whispers of nuclear potential, and the looming shadow of global conflict. To understand its inception, we must step into the laboratories of early 20th century Europe, where the secrets of the atom were slowly being revealed. Physicists like Ernest Rutherford, Niels Bohr, and Albert Einstein probed the structure of matter with curiosity and caution, unaware that their discoveries would one day set humanity on a path toward both incredible power and existential risk. The story truly began in the 1930s, when scientists discovered nuclear fission, the process by which the nucleus of an atom splits into smaller parts, releasing a massive amount of energy. Lise Meitner, Otto Hahn, and Fritz Strassmann were at the forefront of this revelation. They realized that splitting a uranium nucleus could release energy millions of times greater than conventional chemical reactions, a discovery both exhilarating and terrifying. The energy of the atom, once theoretical, had become tangible. At first, the concept of weaponizing fission seemed almost unthinkable. The world was still coming to terms with conventional explosives, and the idea that a single bomb could destroy an entire city stretched the imagination. Yet, as political tensions in Europe escalated, scientists began to recognize the potential implications of nuclear energy in warfare. The rise of Nazi Germany, in particular, spurred a sense of urgency. What if a totalitarian regime harnessed this power before the rest of the world? This question would ultimately catalyze the creation of the Manhattan Project. In 1939, Albert Einstein and physicist Leo Szilard penned a letter to President Franklin D. Roosevelt, warning that Germany might be attempting to build an atomic bomb. Though Einstein himself was a pacifist, the letter highlighted the need for careful scientific and political attention. This correspondence, now iconic, became a spark that ignited governmental action. The United States recognized that it could not ignore the scientific breakthroughs that were rapidly evolving overseas. The Manhattan Project officially began as a coordinated effort to explore nuclear energy for military purposes. Initially, it was small, secretive, and experimental. Scientists across the United States, Britain, and Canada were quietly recruited to study uranium enrichment, chain reactions, and the properties of newly discovered isotopes. Laboratories were established in remote locations to maintain secrecy, and each site specialized in a critical component of the project. Oak Ridge focused on uranium enrichment, Hanford on plutonium production, and Los Alamos on bomb design and assembly. The early stages of the project were filled with both excitement and trepidation. Every experiment carried unknown risks. Physicists and chemists meticulously calculated critical masses, chain reactions, and neutron behavior. The fear was not just theoretical. A miscalculation could lead to an accidental detonation, radiation exposure, or the release of radioactive material. Yet these scientists pressed on, guided by curiosity, duty, and a profound awareness of the stakes involved. Their work required both precision and patience, as they sought to unlock the secrets of a force far greater than anything humankind had previously encountered. Scientific discovery was matched by intense engineering challenges. Enriching uranium to a level suitable for a bomb required monumental effort, innovative machinery, and unprecedented scale. Plutonium production, similarly, involved building reactors capable of sustaining nuclear reactions safely and efficiently. The Manhattan Project became as much an engineering marvel as a scientific one. It demanded collaboration among hundreds of engineers, technicians, and laborers, each contributing to a vast, interdependent system. Amid the technical challenges, ethical questions quietly emerged. Some scientists understood that their work would produce a weapon capable of unimaginable destruction. Debates surfaced about whether the United States should pursue development of the bomb or focus solely on nuclear energy for peaceful purposes. Yet the urgency imposed by war often outweighed these considerations. Many believed that failing to act would leave the world vulnerable to the potential use of nuclear weapons by adversaries. The tension between moral reflection and wartime necessity became a defining feature of the Manhattan Project from its earliest days. The recruitment of top scientific minds added another layer of depth to the project. Figures like Robert Oppenheimer, Enrico Fermi, and Niels Bohr brought extraordinary expertise and vision. Oppenheimer, often described as a contemplative and intense leader, became the intellectual anchor of Los Alamos. Fermi, a master of both theory and experiment, provided practical insight into reactor design. Bohr, who had fled Europe, contributed not only knowledge of nuclear physics, but also philosophical perspectives on the implications of atomic energy. Together, these individuals created a dynamic environment where ideas flowed freely, even as secrecy constrained their world. It was in this context, a world of war, uncertainty, and discovery, that the Manhattan Project transformed from concept to reality. Experiments with uranium and plutonium began to yield critical data. Calculations about bomb design became more refined. Enrichment facilities and reactors started producing measurable amounts of fissile material. Each step brought humanity closer to controlling a force that could destroy cities in an instant. Yet, within the labs and desert sites, there was a sense of quiet purpose. The scientists worked with precision and calm, as if aware that their efforts would echo through history. By the end of the project's early phase, it was clear that a new era was approaching. The Manhattan Project had evolved from a theoretical exploration into a tangible, high-stakes experiment. The atom, once hidden in the core of matter, was now at humanity's fingertips. The project's leaders and participants understood that they were walking a razor's edge between creation and destruction, discovery and devastation. Their work would soon culminate in the first controlled nuclear explosion, a moment that would change the world forever. Even at this early stage, the Manhattan Project exemplified the paradox of human endeavor. Immense danger paired with profound calm, destructive potential tempered by careful calculation. Scientists, engineers, and workers moved forward with dedication and foresight, aware that each measurement, each refinement, and each experiment could have consequences far beyond the desert labs. The Manhattan Project was not only a story of nuclear physics, but also a meditation on human ingenuity, responsibility, and the delicate balance between knowledge and power. Section 2. The Secret Cities, Life and Labor Behind the Manhattan Project. To understand the Manhattan Project fully, one must step beyond equations and nuclear reactions and into the hidden worlds where its human endeavor unfolded. The project was not confined to a laboratory or a single location. It was a sprawling network of secret cities, each meticulously designed to house, feed, and protect thousands of workers and scientists. These communities were both extraordinary and ordinary, a mix of groundbreaking science and daily life, cloaked in the extraordinary secrecy of one of the most dangerous experiments in history. Los Alamos, New Mexico, was the heart of bomb design and assembly. Tucked away in the rugged Jemez Mountains, it became a city devoted entirely to science. Barbed wire and guard towers ensured that outsiders remained unaware of the work taking place within. Yet inside the gates, life continued in a strangely normal rhythm. Scientists' families lived in modest homes, children attended schools, and community centers hosted social gatherings. There was a quiet routine amid the extraordinary work. Laundry was done, meals were cooked, and friendships formed, all while some of the most profound and dangerous experiments in history occurred just miles away. Oak Ridge, Tennessee, presented a very different picture. It was a city built from scratch in record time, designed to accommodate tens of thousands of workers dedicated to enriching uranium. Here, the daily grind of industrial labor intersected with the edges of theoretical physics. Massive buildings housed electromagnetic separation plants, while workers in protective gear carefully monitored machinery that handled radioactive materials. Though the workers often had little understanding of the ultimate goal, they were acutely aware that they were part of something secret, significant, and potentially world-altering. Hanford, Washington, specialized in plutonium production, a process that required unprecedented engineering and meticulous control. Nuclear reactors were constructed along the Columbia River, and the surrounding area became a labyrinth of industrial facilities, barracks, and support structures. Safety protocols were extensive, yet never entirely foolproof, as the workers handled materials that emitted radiation invisible to the eye. Despite these dangers, life continued in a rhythm shaped by the needs of the project. Early morning shifts, careful measurements, and communal meals, all under the constant awareness that their labor was contributing to a weapon of unimaginable power. The scale of human effort across these secret cities was staggering. Tens of thousands of scientists, engineers, laborers, and support staff were mobilized, each performing tasks critical to the success of the project. Women played essential roles in administrative work, mechanical operation, and laboratory assistance, quietly ensuring that the enormous machinery of the project functioned smoothly. Men operated heavy equipment, conducted experiments, and maintained security, all while knowing that the culmination of their work could release energy on a scale no human had ever witnessed. The social dynamics within these secret cities were unique. Individuals from diverse backgrounds, nationalities, and disciplines were brought together, often for the first time. Collaboration was intensive. Brilliant minds debated bomb designs in the evenings, walked the hills discussing chain reactions, and tested theories with a combination of caution and excitement. Yet the pressure of secrecy and the magnitude of the stakes created a constant undercurrent of tension. Conversations about work often had to be carefully measured, even among friends and family, to ensure that no sensitive information slipped beyond the perimeter. Daily life in the secret cities had a rhythm shaped by the extraordinary nature of the work. Scientists like Robert Oppenheimer, Enrico Fermi, and Richard Feynman moved between theoretical discussions and hands-on experimentation, balancing the abstract with the practical. Engineers calibrated machinery, technicians maintained reactors, and administrative staff coordinated logistics across thousands of people. Even recreation had to accommodate secrecy. Social gatherings were permitted but closely monitored, and mail was carefully censored. Yet despite these restrictions, a sense of community emerged, a shared purpose that bound together people who were aware, on some level, that they were participants in history. The psychological dimension of life in these cities was significant. Workers and scientists understood the magnitude of the Manhattan Project, even if they did not know every detail. Anxiety, curiosity, and awe existed side by side. Some wrestled with the ethical implications of their work, pondering the consequences of creating a weapon capable of mass destruction. Others focused on the technical challenges, finding solace in equations, measurements, and mechanical precision. Together, these individuals maintained a delicate balance between dedication and the quiet human need for calm and normalcy. Security measures amplified the sense of isolation. Travel in and out of the sites was heavily restricted, and identity verification was constant. The buildings themselves were designed to obscure the nature of experiments. Workers might operate complex machinery without knowing the ultimate purpose. Scientists might perform calculations whose real-world consequences were hidden. This veil of secrecy, while necessary, created a psychological landscape in which trust, discretion, and professionalism became as vital as scientific skill. Despite the extraordinary circumstances, life in the Manhattan Project cities was not devoid of creativity, camaraderie, or reflection. Scientists played music, wrote poetry, and shared stories of previous research. Families planted gardens, hosted community events, and celebrated birthdays, even amid a project that would reshape human history. Human rhythms persisted. Moments of play, conversation, and quiet thought providing respite from the weight of the work. These moments underscored the paradox of the Manhattan Project. It was simultaneously a hub of immense destructive potential and a space where human ingenuity and resilience thrived. The Manhattan Project's secret cities remind us that large-scale scientific endeavors are deeply human enterprises. They are not merely collections of experiments and machines, but communities in which curiosity, creativity, responsibility, and moral reflection converge. The daily labor of thousands, performed with diligence and care, made the unprecedented control of atomic energy possible. Every careful measurement, every shift of machinery, every late-night discussion in a Los Alamos office contributed to an experiment whose consequences would soon extend far beyond the fences of these secret cities. Ultimately, the secret cities of the Manhattan Project were more than logistical necessities. They were crucibles of human ingenuity and moral contemplation. Within their boundaries, humanity faced a new reality: the ability to harness forces previously considered divine or unattainable. The calm, meticulous work of thousands of individuals created a structure capable of containing and channeling this power, at least temporarily, until the first bomb would demonstrate just how far human understanding and ambition could reach. In these cities, science, secrecy, and society merged. The Manhattan Project was not only an experiment in nuclear physics, it was an experiment in human organization, ethics, and perseverance. The lives of those who walked its streets, tended its machinery, and calculated its equations remind us that behind every great scientific achievement lies the human story, complex, careful, and profoundly consequential. Section 3. Harnessing the Atom, Technical Challenges and a Path to the Bomb. By the time the Manhattan Project was fully underway, the theoretical foundation for an atomic bomb was established, but the practical challenges of turning theory into reality were immense. The scientists and engineers faced a world of unknowns, navigating untested physics, experimental engineering, and unprecedented safety concerns. Every step required precision, patience, and a calm rigor, for even minor errors could result in disaster or failure. The first challenge was obtaining fissile material. Uranium-235 and plutonium-239, the isotopes capable of sustaining a chain reaction. Uranium-235 makes up less than 1% of natural uranium, requiring large-scale separation processes to concentrate it. At Oak Ridge, engineers developed and operated 3 sophisticated methods: electromagnetic separation, gaseous diffusion, and thermal diffusion. Each approach was slow, painstaking, and susceptible to technical failures. Workers monitored massive machines that hummed, clanged, and radiated both heat and danger, often without fully understanding the scale of the task. Yet their disciplined attention to detail kept the project moving forward. Plutonium presented a different challenge. Unlike uranium, it did not occur naturally and had to be produced in nuclear reactors. Hanford's reactors were the first of their kind, designed to convert uranium-238 into plutonium through neutron bombardment. The process required careful control of temperature, radiation, and chemical extraction methods. Workers handled highly radioactive materials, often in shielded facilities, relying on remote manipulation and strict safety protocols to avoid contamination. The quiet precision with which these tasks were performed belied the danger present in every step. Once fissile material was produced, the next challenge was designing a bomb that would achieve a controlled chain reaction. The simplest concept, bringing a critical mass of fissile material together, was deceptively complex. Scientists had to calculate the exact geometry, density, and timing to ensure the reaction would sustain itself without fizzling prematurely. This required balancing theoretical models with experimental validation, an iterative process that demanded both intellectual rigor and meticulous record-keeping. Two distinct designs emerged: the gun type and the implosion design. The gun type, ultimately used in the uranium bomb dropped on Hiroshima, involved firing one piece of uranium into another at high speed to achieve a critical mass. The implosion method, used in the plutonium bomb at Nagasaki, relied on a symmetrical compression of plutonium using conventional explosives to reach the critical density needed for detonation. Both designs were theoretically sound, but untested at scale. Engineers and scientists had to ensure that timing, alignment, and explosive forces were precise, down to microseconds and millimeters. A feat requiring extraordinary coordination and technical ingenuity. Critical experiments were conducted to understand neutron behavior, initiation methods, and material properties. Scientists built small-scale test assemblies, using non-fissile materials to model behavior before handling dangerous quantities of uranium or plutonium. These tests required careful observation, extensive calculations, and patience, as even minor variations could produce misleading results or catastrophic outcomes. Every experiment was a balance of curiosity and caution, where the line between discovery and disaster was remarkably thin. Another technical challenge was controlling the chain reaction itself. Nuclear reactions can escalate almost instantaneously, releasing energy at incredible rates. To prevent premature detonation, scientists designed and tested tamper materials, neutron reflectors, and explosive lenses to focus energy precisely. Simulations and calculations were conducted repeatedly, often by hand or with the primitive computing machines of the era. The team's ability to maintain calm, deliberate work under pressure was as critical to success as any theoretical breakthrough. Handling fissile materials presented further dangers. Uranium and plutonium are highly radioactive, capable of causing acute illness or long-term health effects. Protective measures were developed, including glove boxes, remote manipulators, lead shielding, and stringent protocols for waste disposal. Workers were trained meticulously, monitored closely, and often isolated from each other to prevent contamination. Despite these precautions, the constant awareness of risk created a quiet tension that permeated the laboratories. Every movement, every adjustment had to be precise. Errors could expose both individuals and the project to dangerous consequences. The technical challenges were matched by logistical and environmental complexities. Enrichment plants, reactors, and laboratories required enormous amounts of electricity, water, and cooling systems. Buildings had to be constructed in remote areas, often in extreme weather, while maintaining secrecy. Materials had to be transported discreetly, sometimes across states, or through heavily guarded convoys. Communication between sites was tightly controlled, yet coordination had to be flawless to synchronize production schedules, experiments, and delivery of fissile material. The scale of the Manhattan Project was unparalleled, making logistics as formidable a challenge as physics or engineering. Throughout this technical endeavor, human ingenuity and collaboration were paramount. Teams of scientists, engineers, and laborers shared knowledge across disciplines, troubleshooting complex problems with creativity and precision. Discussions extended into evenings, weekends, and informal gatherings as minds grappled with the unknown. In this environment, discovery and caution coexisted. Every calculation was checked multiple times, every design scrutinized, and every experiment approached with a respect for both its potential and its danger. The culmination of these efforts was both the successful assembly of functional bombs by the summer of 1945. The journey from theory to practical device was a testament to meticulous planning, intellectual rigor, and unwavering focus. The Manhattan Project had transformed abstract physics into tangible power, producing weapons that could release energy on a scale previously unimaginable. Yet behind the technical achievement lay a deeper lesson. The combination of knowledge, responsibility, and careful human labor was as essential as any calculation in controlling forces that could reshape the world. In reflecting on the technical challenges of the Manhattan Project, one is struck not only by the ingenuity required, but also by the quiet intensity with which it was conducted. Scientists and engineers moved deliberately, aware that every measurement, every alignment, and every decision could have monumental consequences. The Manhattan Project exemplifies the paradox of human innovation: profound potential for creation and destruction, navigated with patience, care, and an almost meditative focus on precision. Section 4. The Trinity Test: Witnessing the Birth of the Atomic Age. By mid-1945, the Manhattan Project had moved from theory and preparation to the brink of a historic experiment, the first detonation of an atomic bomb. Known as the Trinity Test, it was not merely a scientific trial. It was a moment that would mark the birth of a new age, one in which humanity could wield forces previously confined to the stars. Hidden in the deserts of New Mexico, the test site became a quiet stage for a profound and unprecedented demonstration of both human ingenuity and caution. The location was carefully chosen. The Jornada del Muerto Desert offered remoteness, isolation, and a sparse population. It provided a landscape where the energy unleashed by the bomb could be measured without immediate risk to human settlements. Even so, precautions were meticulous. Scientists, military personnel, and observers were stationed at calculated distances, with shelters and observation posts designed to minimize exposure to heat, radiation, and debris. The desert, silent and vast, was the perfect witness to an experiment of unimaginable magnitude. In the hours leading up to the test, the atmosphere was a blend of tension, anticipation, and quiet reflection. Robert Oppenheimer, the scientific director of the Manhattan Project, walked among the assembled scientists, technicians, and military officers. Conversations were muted, voices careful, and every movement deliberate. Equipment was checked repeatedly. Timing mechanisms, measuring devices, cameras, and instruments were scrutinized for even the smallest anomalies. The entire operation demanded a balance of patience and precision, as any oversight could compromise both safety and the validity of the experiment. At 5:29 a.m. on July 16, 1945, the plutonium bomb, codenamed the Gadget, was detonated atop a 100-foot steel tower. For a brief instant, the desert horizon was transformed. A brilliant flash lit the sky, surpassing the intensity of the sun, followed by a mushroom cloud that climbed tens of thousands of feet. The heat was so intense that observers reported feeling it on their faces from miles away. Seismographs detected the shock, and instruments recorded energy releases far beyond conventional explosives. It was the culmination of years of painstaking work, the tangible realization of human understanding applied to the atom. The immediate aftermath was surreal. Those present described a moment of awe, fear, and reflective silence. The desert seemed both unchanged and utterly transformed, as if reality itself had shifted. Oppenheimer later recalled a line from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." Though he said it with a sense of philosophical reflection rather than theatricality, it captured the profound weight of what had just occurred. Humanity had released an energy that could reshape civilization itself. Scientists and engineers quickly moved to analyze the results. Data confirmed the success of the implosion method for plutonium, validating years of theoretical calculations and meticulous engineering. Neutron flux, energy yield, and explosive performance were carefully measured. The observations provided not only proof of concept, but also insights for improving design, efficiency, and safety in future applications. Every detail, from the behavior of the blast to the formation of the mushroom cloud, became critical information for both scientific understanding and military planning. The psychological impact on those present was as significant as the technical achievement. Many of the scientists were struck by the paradoxical calm of the moment amid extraordinary energy release. The desert returned to silence almost immediately, leaving only scorched sand, displaced earth, and the echoes of sound and heat. Observers described a mix of relief, awe, and existential contemplation. For some, it was a triumph of human intellect and perseverance. For others, it was a profound reminder of the responsibilities inherent in wielding such power. While the Trinity test was a controlled experiment, its implications for the wider world were undeniable. The success meant that the United States now possessed the ability to end wars in a way previously unimaginable, but also the ability to inflict devastation on a scale never before witnessed. The scientists and military personnel understood that this was no ordinary weapon. It represented a turning point in history, a demonstration of what human curiosity, ingenuity, and focus could achieve when applied to nature's most fundamental forces. The calmness with which the Manhattan Project team approached the Trinity test underscores a paradox at the heart of scientific exploration. The detonation was a moment of immense power, yet it was preceded and followed by meticulous planning, methodical observation, and careful analysis. The desert, silent witness to the first atomic explosion, became a space for reflection as much as measurement. Human intellect had unlocked the atom, but with it came a profound responsibility to understand and, if possible, control the consequences. The Trinity test also illustrated the delicate balance between secrecy and collaboration. Despite the magnitude of the experiment, only a few knew the full details. Coordination across laboratories, sites, and teams had to be flawless, yet individual participants often focused solely on their own areas of expertise. The result was a tapestry of human effort and trust, where countless small, precise contributions combined to produce a singularly transformative event. As the sun rose higher over the New Mexico desert, the desert sands cooled, and the initial shockwaves of the blast dissipated. Yet the implications rippled outward through laboratories, cities, and nations. The Manhattan Project had demonstrated that the atom could be harnessed, controlled, and if unleashed in conflict, could alter the course of human history. The calm, deliberate work of thousands had culminated in a flash of extraordinary energy, illuminating both the potential and the peril of scientific progress. Even decades later, the Trinity test is remembered not just for its technical achievement, but for the reflective quiet that surrounded it. It was a moment of measured observation amid monumental energy release, a symbol of the paradox of human discovery. The Manhattan Project had succeeded in mastering the atom, but in doing so, had also opened the door to questions that continue to challenge humanity. How should such power be wielded? Who bears responsibility for its consequences? And what does it mean to hold the forces of nature in human hands? Section 5. Ethics in the Desert. The Moral Dilemmas of the Manhattan Project. The Manhattan Project was not only a triumph of science and engineering, it was also an unparalleled exercise in ethical reflection. Beneath the hum of machinery, the meticulous measurements, and the hush of secret laboratories, a quieter but no less vital discussion unfolded. Should the bomb be used, and if so, under what circumstances? Scientists, military leaders, and political figures were acutely aware that their work had moved from theory to a force capable of instant and irreversible destruction. Ethical debates began long before the first bomb was assembled. Some scientists, including Leo Szilard and Joseph Rotblat, expressed concern about the potential human cost of using atomic weapons. They imagined the casualties, the cities flattened, and the lives extinguished in a single moment. Others argued that the bomb could end the war swiftly, saving countless lives that would otherwise be lost in a prolonged conflict. These discussions were never purely abstract. They were grounded in the immediacy of wartime necessity, the realities of military strategy, and the unknown future of global power dynamics. Within Los Alamos, ethical questions were as present as scientific ones. Robert Oppenheimer, though deeply committed to scientific progress, often reflected on the moral weight of his leadership. He understood that the work being done was not neutral. It was creating a weapon that could redefine human civilization. Quietly, he and other leaders considered how to reconcile the pursuit of knowledge with the responsibility for potential destruction. Conversations were often private, held in offices, hallways, or during long walks in the New Mexico desert, where the stillness allowed space for contemplation. The scientists' sense of urgency was palpable. The fear that Nazi Germany might develop an atomic bomb first added pressure, creating a moral tension between preventative action and the potential cost of using such a weapon. Some argued that developing the bomb was a necessary safeguard, a deterrent against even greater devastation. Others feared that once unleashed, the technology would set a precedent for future conflict, embedding unprecedented destruction into the very fabric of international relations. Even among military leaders, the ethical weight of the bomb's use was clear. Plans were developed to deploy it strategically, to maximize impact on enemy morale and minimize American casualties. Yet these calculations could not escape the human consequences. Hundreds of thousands of civilian lives would inevitably be affected. Behind every map, every target, every calculation, lay the quiet awareness of immense responsibility. The Manhattan Project was not simply a technical endeavor. It was a meditation on the power of knowledge and the human capacity to wield it. Debates extended beyond the desert laboratories to meetings in Washington, D.C., where scientists and military leaders discussed timing, targets, and potential alternatives. Szilard and a small group of scientists petitioned for a demonstration on an uninhabited island, hoping to show the bomb's power without causing mass casualties. Others believed that any such delay would be politically or militarily untenable, and that demonstrating restraint might embolden enemy resistance. These discussions highlighted a paradox. The more powerful the weapon, the more profound the ethical considerations, and yet the pressures of war often compressed reflection into fleeting moments. The moral dilemmas of the Manhattan Project were compounded by secrecy. Scientists could not discuss their work openly, even with friends or family. The isolated nature of Los Alamos, Oak Ridge, and Hanford intensified the internal struggle. Individuals had to reconcile the abstract reality of their calculations with the knowledge that their work could soon take tangible human lives. The calm, precise labor in laboratories was juxtaposed against the inner tension of ethical responsibility, creating a unique psychological landscape that few other projects in history have mirrored. For many participants, reflection became a personal, almost meditative practice. Walking in the desert, observing the mountains, or staring at the night sky offered moments to consider the consequences of atomic energy. Letters, journals, and private conversations reveal a consistent theme. The pursuit of knowledge was inseparable from questions of morality. Scientists wrestled with whether mastery of the atom was a triumph or a curse, and whether their role was to create, to warn, or to advocate restraint. The use of the bomb would ultimately be decided not solely by scientists, but by political and military leaders. Yet the ethical debates among the Manhattan Project participants left a lasting imprint. They shaped post-war reflections on science and responsibility, contributed to the founding of organizations dedicated to nuclear disarmament, and influenced generations of scientists in considering the broader implications of their work. The Manhattan Project was thus both a technological and ethical experiment. It tested not only what humans could do, but also how they would reckon with the consequences. The paradox of the Manhattan Project lies in the coexistence of calm and catastrophe. In the laboratories and secret cities, meticulous calculations, careful measurements, and steady hands prevailed. Outside, the specter of immense destruction loomed, forcing continuous moral reflection. The scientists' and engineers' ability to work with composure, despite understanding the potential consequences, exemplifies the delicate balance between knowledge and responsibility, a balance that remains profoundly relevant today. In contemplating the ethical dimension of the Manhattan Project, one sees that the story of science is inseparable from the story of humanity. The bomb was not merely a product of equations and engineering. It was an artifact of human choice, deliberation, and reflection. The quiet debates in offices, laboratories, and desert paths demonstrate that even in moments of immense pressure and historical urgency, individuals wrestled with profound questions of morality, responsibility, and the cost of wielding unprecedented power. Ultimately, the ethical challenges faced by the Manhattan Project participants serve as a timeless reminder. Knowledge, once acquired, carries responsibility, and human ingenuity, no matter how disciplined or calm, can produce both creation and destruction. The Manhattan Project exemplifies the tension between possibility and consequence, a meditation on the delicate equilibrium between human curiosity and ethical awareness, and the quiet, reflective labor that underpins even the most extraordinary technological achievements. Section 6. Hiroshima and Nagasaki. Observing the unimaginable. The culmination of the Manhattan Project's years of painstaking work arrived in August 1945, not in a laboratory or desert testing site, but over the cities of Hiroshima and Nagasaki. For the scientists and engineers who had labored in secret, the detonation of the bombs in populated areas was a moment of both scientific observation and profound human reckoning. In those minutes, theory met reality, and the consequences of decades of research became undeniably tangible. On August 6, 1945, the B-29 bomber Enola Gay released the uranium bomb, nicknamed Little Boy, over Hiroshima. From thousands of feet above, the city appeared calm, unaware of the extraordinary force about to descend upon it. For the scientists who had studied chain reactions and critical masses, the precise release of the bomb represented the realization of countless calculations, tests, and refinements. Instruments on the plane recorded blast parameters, thermal radiation, and the initial cloud formation, translating human curiosity into empirical observation. Yet for all the data collected, the human impact, the sudden annihilation of tens of thousands of lives, was beyond prediction or quantification. The immediate aftermath in Hiroshima was stark and surreal. Within moments, structures were flattened, fires erupted, and shock waves radiated across the city. The scale of destruction was almost incomprehensible. Hospitals, schools, homes, and businesses vanished in an instant. Scientists, stationed far from the blast but monitoring instruments, noted the extraordinary energy released. the mushroom cloud's rapid formation, and the patterns of thermal radiation. For them, it was a confirmation of theory. For the world, it was a profound and tragic demonstration of the atom's destructive potential. 3 days later, on August 9th, the plutonium bomb, Fat Man, was dropped on Nagasaki. The landscape there differed from Hiroshima's, and the bomb's implosion design behaved according to calculated predictions. Observers recorded shock waves, fireball formation, and initial radiation levels. Scientists analyzed the data in real time, comparing it with predictions from Los Alamos, confirming the reliability and precision of the implosion method. Each measurement, each observation, was a mixture of scientific triumph and quiet horror, as the human consequences were instantly visible through news reports and communications from the field. Despite the focus on technical and empirical data, many Manhattan Project scientists were deeply affected emotionally by the bombings. Letters, memoirs, and interviews from the years following reveal a mixture of awe, fear, and moral contemplation. Some took solace in the idea that the bombings contributed to ending the war, potentially saving lives that would have been lost in a prolonged conflict. Others wrestled with guilt and the ethical implications of creating a weapon capable of such instantaneous devastation. The serene labor of the laboratories and the desert testing grounds contrasted sharply with the chaos and suffering now recorded in the cities below. Medical observations following the bombings provided further insight into the destructive reach of nuclear weapons. Doctors and researchers documented injuries caused by blast waves, thermal radiation, and acute radiation exposure. Burns, fractures, and internal organ damage occurred on an unprecedented scale. Radiation sickness appeared hours and days later, affecting survivors in ways that scientists had theorized but had not witnessed firsthand. The Manhattan Project's participants, while primarily focused on physics and engineering, were forced to confront the tangible human consequences of their work, a sobering extension of the experiment they had so carefully controlled in laboratories. The bombings also revealed the unpredictable elements of nuclear energy. Weather conditions, city layouts, and building materials all influenced the extent of damage and human suffering. Shadowed imprints of individuals who had been in the path of the thermal pulse became haunting symbols of the sudden, precise, and indiscriminate force of the explosion. For scientists accustomed to controlled experiments, these variables underscored the unpredictability inherent in applying theoretical power to complex living systems. Human life, structures, and environmental conditions could not be fully modeled or anticipated, no matter how exact the calculations. While many of the Manhattan Project scientists understood the technical success, the scale of human impact left a lasting impression. Oppenheimer and others reflected on the moral weight of unleashing nuclear energy on populated areas, a weight that would shake scientific ethics for generations. The experience highlighted a central paradox of human knowledge. The capacity to understand and manipulate the universe comes with responsibilities that extend far beyond calculation tables, laboratory walls, or secret cities. Precision and calm in scientific work
could yield both extraordinary insight and devastating consequences when applied to real-world contexts. The bombings also altered the perception of war, science, and human potential. The scale of destruction measured scientifically and witnessed by survivors
Established nuclear weapons as a distinct category of human capability, one that transcended conventional warfare and demanded new approaches to diplomacy, policy, and ethical consideration. Manhattan Project scientists became not only engineers and physicists, but also observers of history, documenting the effects of their work while contemplating its moral and societal implications. In the quiet of offices, laboratories, and homes far from the blast sites, participants reflected on the paradoxical nature of their achievement. The calm, methodical work that had led to the bombs now existed alongside the sudden and uncontrollable release of energy in the cities below. The precision and care of years of labor had produced not only scientific validation, but also a human tragedy. This juxtaposition of calm observation and profound consequence encapsulates the dual legacy of the Manhattan Project, a triumph of knowledge intertwined with an enduring ethical responsibility. Ultimately, the bombings of Hiroshima and Nagasaki transformed the Manhattan Project from a secret scientific endeavor into a global historical event. They demonstrated the astonishing potential of human ingenuity to manipulate the fundamental forces of nature, while also reminding the world that the application of such knowledge carries profound consequences. Observing the immediate and long-term effects, scientists were forced to confront questions that would echo for decades. How should such power be used? What responsibilities accompany scientific discovery? And how can humanity balance curiosity, capability, and conscience in the face of forces previously unthinkable? Section 7. Global shockwaves. The immediate reactions to the atomic bomb. The detonation of atomic bombs over Hiroshima and Nagasaki sent ripples far beyond the islands of Japan, reaching every corner of the globe. News of the bombings arrived like a sudden, blinding flash. Journalists, governments, scientists, and citizens alike struggled to comprehend both the technical achievement and the moral implications. The Manhattan Project, once a secretive endeavor confined to laboratories, secret cities, and desert test sites, had suddenly thrust humanity into a new era, an era defined by unprecedented destructive potential and global ethical dilemmas. For the scientific community, the reactions were a complex blend of astonishment, concern, and reflection. Physicists and engineers who had devoted years to understanding chain reactions and critical masses now observed the practical realization of their work on a scale never imagined. Reports detailing the energy released, blast radius, and thermal effects confirmed the theoretical predictions from Los Alamos. Yet, the human toll rendered the data both awe-inspiring and horrifying. Many scientists found themselves grappling with conflicting emotions. Pride in the technical success, tempered by the moral weight of its consequences. Internationally, governments immediately recognized the transformative nature of nuclear technology. Political leaders debated strategy, potential threats, and the balance of power. The United States emerged as a nuclear power overnight, while other nations, including the United Kingdom, the Soviet Union, and Germany's remnants, assessed the implications for global security. The bombings signaled a fundamental shift in warfare and diplomacy, introducing the concept of mutually assured destruction long before the Cold War's tensions fully crystallized. Leaders realized that traditional military strategies had become inadequate in the face of nuclear capability, and urgent discussions began regarding arms control, intelligence sharing, and future deterrence. Media coverage played a crucial role in shaping public perception. Newspapers, radio broadcasts, and photographs conveyed both the technical marvel and human tragedy. Images of flattened cities, shadowed imprints on walls, and injured survivors stunned readers around the world. For many, the atomic bomb symbolized both the pinnacle of human ingenuity and the terrifying potential of scientific knowledge untempered by moral reflection. The duality was unmistakable. An extraordinary scientific achievement intertwined with unprecedented human devastation. The bombings also sparked immediate debate among scientists themselves. Some advocated for public disclosure, arguing that society needed to understand the consequences of the new technology. Others supported continued secrecy, emphasizing security concerns and the desire to maintain a strategic advantage. These discussions highlighted the tension between transparency and safety, illustrating how the pursuit of knowledge can be both empowering and morally fraught. The Manhattan Project, once a carefully controlled experiment in secret, now faced the challenge of contextualizing its legacy in a rapidly changing world. Ethical concerns surged alongside scientific interest. International conferences, private correspondence, and public debates began to explore the responsibility of scientists for the uses of their discoveries. Figures such as Niels Bohr and Albert Einstein emphasized the need for global cooperation and dialogue to prevent catastrophic misuse. Meanwhile, U.S. scientists formed advisory committees and ethical councils to reflect on the implications of nuclear energy, advocating for caution in both experimentation and policy. These discussions marked a new phase of scientific responsibility, awareness that discovery without moral reflection could unleash forces beyond human control. The global reaction was not confined to the scientific or political elite. Ordinary people around the world struggled to grasp the magnitude of what had occurred. Letters, diaries, and news reports reveal widespread fascination, fear, and contemplation. Children, adults, and families considered how the atomic bomb could alter daily life, warfare, and even the trajectory of civilization itself. The sudden visibility of nuclear power transformed abstract physics into a tangible, even existential force that touched hearts and minds far beyond laboratory walls. For many, the atomic bomb raised profound philosophical questions. The concept that humans could release energy equivalent to the power of the sun in controlled form
challenged traditional notions of human capability, responsibility, and morality.
Ethical considerations, once confined to theoretical debate, now demanded practical decisions about war, peace, and survival. The world's awareness of the bomb brought both awe at human ingenuity and anxiety about the fragile balance between creation and destruction. The immediate global response also included scientific curiosity about long-term effects, radiation sickness, environmental impact, and ecological consequences became subjects of urgent study. Physicians, engineers, and physicists collaborated to understand the physical aftermath, translating observations into knowledge that could inform safety standards, future planning, and disaster mitigation. While these studies were methodical and deliberate, they were conducted under the shadow of urgency. Humanity had witnessed a power that could alter the very landscape of civilization, and careful understanding was essential. In the aftermath, the Manhattan Project's legacy extended beyond technology to encompass moral, political, and societal dimensions. It became a case study in the profound responsibilities that accompany scientific achievement. The calm, meticulous work in laboratories and secret cities had produced results of both breathtaking precision and staggering consequence. Observing these results, the world realized that science had entered a new phase, no longer confined to curiosity-driven exploration. It now carried the weight of global ethical responsibility. Ultimately, the immediate global reaction to the atomic bombings was a mixture of wonder, fear, and reflection. Scientists, governments, and ordinary citizens alike recognized the dual nature of the achievement: a technical triumph revealing the boundless potential of human knowledge, and a stark reminder that such power demands contemplation, restraint, and moral courage. The Manhattan Project, once a secretive experiment in physics and engineering, had transformed into a worldwide meditation on the limits, responsibilities, and consequences of human discovery. Section 8. Long Shadows: The Lasting Scientific and Societal Impact of the Manhattan Project. The Manhattan Project, while originally a wartime endeavor, cast long shadows that stretched far beyond the laboratories and desert test sites. Its influence permeated not only science and engineering, but also society, ethics, politics, and the global consciousness. Decades later, the calm, meticulous work conducted in secret became the foundation for both technological progress and ongoing reflection on the responsibilities of human knowledge. One of the most immediate and tangible scientific legacies was the advent of nuclear physics as a central field of research. The Manhattan Project accelerated understanding of atomic structure, neutron behavior, chain reactions, and nuclear fission. Techniques developed for uranium enrichment, plutonium production, and detonation design were later adapted for civilian energy generation. Nuclear reactors, originally built to produce plutonium for weapons, became the cornerstone of atomic energy, research reactors, and medical isotopes. Laboratories once devoted to war research evolved into centers of peaceful exploration, demonstrating how knowledge, carefully stewarded, could be redirected for human benefit. The Manhattan Project also created a model for big science, Large, interdisciplinary, government-funded research projects requiring collaboration across multiple institutions. The scale of coordination between Los Alamos, Oak Ridge, Hanford, and other facilities revealed the potential for organized, large-scale scientific endeavors. This model influenced future projects such as space exploration, particle accelerators, and global climate studies, highlighting the importance of integrating diverse expertise toward a common objective. Yet the project also showed that the power of science is not inherently benevolent. Its applications must be tempered with reflection, ethics, and societal oversight. Ecologically, the Manhattan Project left complex and enduring footprints. Production sites, waste storage, and accidental contamination posed long-term environmental challenges. The uranium enrichment facilities at Oak Ridge and the plutonium production reactors at Hanford generated radioactive byproducts that required decades of monitoring and remediation. Scientists learned, often through trial and error, about the persistence of radioactive isotopes, their movement through water and soil, and the importance of containment. This early experience informed environmental safety protocols for nuclear facilities worldwide, demonstrating that careful observation and analysis can mitigate, though never entirely eliminate, human impact on the natural world. On a societal level, the Manhattan Project reshaped public understanding of science. The bombings of Hiroshima and Nagasaki demonstrated both the power and danger of scientific knowledge, transforming the perception of what humans could accomplish. The project catalyzed discussions about the ethical obligations of scientists, the role of government in directing research, and the need for international cooperation to prevent catastrophic misuse. These debates continue today, reflecting the enduring tension between technological capability and moral responsibility, a tension that the Manhattan Project first brought into sharp relief. The human experience within the Manhattan Project also left a profound legacy. The scientists, engineers, and laborers involved faced intense pressure, secrecy, and ethical dilemmas. The calm, meticulous precision with which they approached their work, often under extreme stress and isolation, became a study in human resilience and the capacity for disciplined focus. Letters, memoirs, and oral histories reveal moments of quiet reflection, walks in the desert, conversations at dusk, or careful observation of small-scale experiments provided respite from the magnitude of their tasks. The project illustrated that scientific discovery is as much a human endeavor as a technical one, shaped by temperament, ethics, and collaboration. The Manhattan Project also sparked the beginnings of organized nuclear policy. Governments and international bodies recognized that atomic energy was not merely a tool, but a force capable of global transformation. Early discussions about arms control, non-proliferation, and strategic deterrence emerged from the awareness of the bomb's destructive power. Institutions like the Atomic Energy Commission in the United States were formed to oversee civilian and military nuclear programs, blending scientific oversight with political governance. This framework established a precedent. Technology of extraordinary power demands structures for accountability,
transparency, and ethical guidance.
Culturally, the Manhattan Project imprinted itself on literature, film, and public imagination. From novels and documentaries to movies and philosophical discourse, society grappled with the duality of human ingenuity. The same knowledge that could illuminate the universe could also extinguish life. Stories emerged not only of technical triumph, but also of human tension, moral reflection, and the quiet struggles of individuals working under secrecy and ethical ambiguity. The calm, deliberate work behind the bomb's creation became a symbol of both human potential and cautionary responsibility. The Manhattan Project also set the stage for ongoing scientific inquiry into the atom and energy. Research into nuclear medicine, particle physics, and energy generation relied on techniques and insights developed during the project. Atomic understanding deepened, leading to innovations in medical imaging, cancer treatment, and even space exploration. Yet alongside these advances, the shadow of nuclear weaponry remained, reminding future scientists that discovery is inseparable from ethical reflection, and that knowledge, once unlocked, has the potential for both benefit and harm. Even in education, the Manhattan Project's legacy endures. Universities and research institutions emphasize interdisciplinary collaboration, ethical responsibility, and large-scale project management in scientific curricula. The story of Los Alamos, Oak Ridge, and Hanford provides case studies in problem-solving under extreme pressure, collaboration across disciplines, and the necessity of ethical reflection. Students learn not only the technical achievements, but also the human, societal, and moral dimensions of scientific discovery, reinforcing the lesson that knowledge is a responsibility as much as a tool. Finally, a Manhattan Project serves as a reminder of the paradox at the heart of human progress. The capacity for calm, disciplined work can yield extraordinary achievements, yet those same achievements can unleash consequences beyond comprehension. The serene focus of scientists in secret laboratories contrasts with the violent and immediate impact of their work on the world stage. This juxtaposition is a timeless meditation on the dual nature of human capability, how careful, precise effort can create both life-enhancing technology and instruments of unimaginable destruction. Section 9. The Cold Dawn. How the Manhattan Project Shaped the Nuclear Era. The end of World War II did not mark the end of the Manhattan Project's influence. Instead, the successful development and deployment of atomic bombs initiated a new chapter in global history. The nuclear era. The calm, meticulous labor of thousands of scientists and engineers in secret cities had transformed the geopolitical landscape, giving birth to both unprecedented technological capability and an enduring climate of strategic tension known as the Cold War. Almost immediately after Hiroshima and Nagasaki, nations recognized the strategic significance of nuclear technology. The United States, having demonstrated the bomb's devastating potential, held a decisive advantage. However, the Soviet Union, aware of the transformative power of atomic energy, accelerated its own nuclear program. Determined not to lag behind, This rapid proliferation set the stage for a tense and prolonged global standoff, wherein the threat of nuclear weapons would shape diplomacy, defense strategies, and international relations for decades. The Cold War was characterized not by direct widespread conflict, but by the constant awareness of mutual vulnerability. The Manhattan Project had shown that a single atomic bomb could devastate a city, and this knowledge was not lost on leaders around the world. Nuclear weapons became tools of deterrence, instruments of geopolitical leverage, and catalysts for an entirely new kind of diplomacy. Countries had to navigate the delicate balance between demonstrating strength and avoiding catastrophe, a dynamic that reshaped political strategy and international law in ways the Manhattan Project scientists could scarcely have imagined. Scientifically, the Cold War spurred an unprecedented acceleration of nuclear research. Weapons designs evolved, becoming more sophisticated and efficient, while delivery systems, ballistic missiles, submarines, and long-range bombers were developed to complement them. Laboratories that had once focused on wartime production pivoted toward long-term innovation, exploring fusion, radiation shielding, and high-energy physics. The Manhattan Project had set a precedent. Carefully orchestrated, large-scale scientific collaboration could produce results far beyond conventional experimentation, and governments quickly recognized the potential value of investing in big science as a tool of both national security and prestige. Alongside these developments, the global ethical and cultural response to nuclear weapons deepened. The awareness of humanity's newfound capacity for instantaneous destruction permeated literature, art, and philosophy. Writers and thinkers grappled with the existential implications of atomic energy, pondering humanity's responsibility to itself and the planet. The calm, disciplined focus that had characterized the laboratories of Los Alamos and Oak Ridge became a stark contrast to the global anxiety that the presence of these weapons provoked. The Manhattan Project, once a secretive technical endeavor, had become a symbol of human ingenuity and moral responsibility on a planetary scale. One of the key legacies of the Manhattan Project during this period was the development of nuclear policy and international governance. The United Nations, the Atomic Energy Commission, and various treaties emerged as mechanisms to regulate the spread of nuclear technology and reduce the risk of catastrophic war. Scientists and policymakers collaborated to establish protocols for inspection, arms control, and knowledge sharing. These efforts reflected a hard-learned lesson. The potential for destruction necessitated structures of oversight, ethical deliberation, and global coordination. The calm logic of laboratory experimentation had given way to the delicate diplomacy of survival. The Cold War also catalyzed significant investment in education and infrastructure for scientific advancement. Universities expanded physics and engineering programs, national laboratories were strengthened, and research funding surged. The Manhattan Project had demonstrated that interdisciplinary collaboration, combining physics, chemistry, engineering, and logistics, could achieve extraordinary outcomes. Governments and institutions replicated this model,
to foster innovation in both civilian and military contexts. In this way, the project's influence extended beyond weapons development, shaping the very way science was conducted and valued across nations. Ecologically and environmentally, the Cold War era revealed further consequences of the Manhattan Project's innovations. Nuclear testing, both atmospheric and underground, introduced new challenges, including radiation exposure, environmental contamination, and health risks for nearby populations. Scientists and policymakers had to develop monitoring, mitigation, and remediation techniques, tasks that required the same meticulous observation and careful analysis that had characterized the original Manhattan Project. Once again, the duality of knowledge became clear. Scientific insight enabled powerful technology, but also demanded vigilance and ethical oversight to manage unintended consequences. Public perception of the nuclear era was deeply influenced by the legacy of the Manhattan Project. The calm, precise work of the scientists contrasted sharply with the existential anxiety felt by populations living under the shadow of potential annihilation. Education campaigns, media coverage, and civil defense initiatives attempted to balance fear with understanding, teaching citizens about fallout shelters, radiation, and emergency preparedness. The Manhattan Project had created not only a technological revolution, but also a psychological one, shaping how society perceived risk, power, and the responsibilities of scientific advancement. Finally, the Cold War underscored the paradoxical nature of human achievement. The same ingenuity that had produced the first atomic bombs could drive exploration, medical innovation, and energy generation. Yet it also created the constant potential for global catastrophe. The Manhattan Project's careful, deliberate work in secret cities and laboratories had illuminated the atom. The Cold War revealed the consequences of that illumination on a planetary scale. The dual legacy, technological mastery, alongside moral vigilance, continues to define humanity's relationship with nuclear power and, more broadly, with the limits of scientific responsibility. In this way, the Manhattan Project did more than create the atomic bomb. It inaugurated an era in which knowledge, power, and ethics are inextricably intertwined. The calm, meticulous labor of scientists became the foundation for global tension, innovation, and ethical reflection, a reminder that extraordinary capability always carries extraordinary responsibility. Humanity learned that understanding nature is only part of the journey. How we choose to wield that understanding shapes history itself.
Section 10. From Destruction to Power. Civilian Nuclear Energy and the Manhattan Project Legacy. While the Manhattan Project is most often remembered for the atomic bombs dropped over Japan, its legacy extends far beyond military applications. The meticulous research, large-scale coordination, and technical innovations that defined the project laid the groundwork for civilian nuclear energy, transforming how humanity harnesses power and shaping a vision of sustainable electricity that was previously unimaginable. The transition from weapons research to peaceful nuclear energy began almost immediately after World War II. Scientists who had once focused on plutonium production and uranium enrichment recognized that the same processes could generate heat for electricity. Early experiments in nuclear reactors demonstrated that controlled fission reactions could produce energy steadily, safely, and on a scale far surpassing traditional fossil fuels. This realization marked a new chapter in human interaction with the atom, from a force of destruction to a source of possibility. The design principles developed at Hanford, Oak Ridge, and Los Alamos proved invaluable for civilian applications. Reactor control systems, cooling methods, and fuel management techniques were adapted to generate electricity in urban centers and industrial sites. The meticulous precision required to prevent uncontrolled reactions in bomb material translated perfectly to the rigorous safety standards necessary for nuclear power plants. The calm, disciplined work of Manhattan Project scientists had inadvertently created the blueprint for an entirely new form of energy production. One of the earliest civilian reactors, the Shippingport Atomic Power Station in Pennsylvania, symbolized this shift. Built in the 1950s, it demonstrated that nuclear fission could be harnessed reliably for peaceful purposes. Observers at the time marveled at the quiet hum of the reactor core, the steady glow of control panels, and the absence of combustion or smoke. Unlike the sudden, violent release of energy in Hiroshima or Nagasaki, the Shippingport reactor exemplified controlled, sustained power, highlighting the potential for nuclear energy to support modern society without catastrophic consequences, if managed responsibly. Beyond electricity, the Manhattan Project's legacy enabled advances in medicine, industry, and scientific research. Radioisotopes produced in reactors facilitated medical imaging, cancer treatment, and sterilization of medical instruments. Laboratories adapted reactor techniques to produce tracers for chemical and biological studies, opening new frontiers in understanding human health and environmental processes. The same atomic knowledge that once prompted ethical debates over mass destruction now empowered researchers to save lives, monitor ecosystems, and expand human knowledge in entirely new ways. The environmental impact of civilian nuclear energy also reflected lessons learned from the Manhattan Project. Early reactors required careful management of waste products, cooling systems, and radiation containment. Engineers and scientists drew on experiences from Hanford and Oak Ridge, applying rigorous safety protocols, continuous monitoring, and innovative engineering solutions to minimize risk. The calm, deliberate methodology of the Manhattan Project, measuring, calculating, observing, adjusting, became essential for ensuring that nuclear energy could be used safely in populated areas, balancing power generation with environmental stewardship. International collaboration emerged as another significant legacy. The Manhattan Project had shown that large-scale, interdisciplinary coordination could yield extraordinary results. Post-war, similar collaborative frameworks were established for civilian nuclear projects. Organizations like the International Atomic Energy Agency, IAEA, encouraged knowledge sharing, safety standards, and peaceful cooperation. Scientists, once working in isolated secret cities, now contributed to global networks of innovation, education, and monitoring, fostering a culture in which knowledge could be both powerful and responsible. Cultural perception of nuclear energy also evolved from the Manhattan Project's influence. Public fascination with atomic science persisted, but the narrative shifted from fear to cautious optimism. Exhibits, documentaries, and educational programs emphasized the peaceful potential of the atom, portraying nuclear reactors as symbols of human ingenuity and progress. At the same time, the shadow of Hiroshima and Nagasaki remained, instilling a deep awareness of responsibility. The calm, precise work behind the Manhattan Project was recontextualized as a reminder that knowledge is a double-edged sword and that careful oversight is essential for translating potential into positive outcomes. The Manhattan Project also inspired technological innovation beyond direct nuclear applications. Advances in metallurgy, chemical engineering, computing, and logistics developed to meet the project's demanding requirements were repurposed for civilian industry. Early computers, initially designed to simulate fission reactions, became the foundation for modern computing. Materials science innovations developed to contain and manipulate radioactive elements, informed aerospace, construction, and energy sectors. The careful integration of disciplines, a hallmark of the Manhattan Project, became a model for complex, high-stakes engineering projects worldwide. Yet, alongside these achievements, the legacy of responsibility remained ever present. The power to manipulate the atom carries inherent risks, from reactor accidents to proliferation concerns. Lessons learned from the Manhattan Project continue to shape policies, training programs, and regulatory frameworks, emphasizing that scientific knowledge, however extraordinary, must always be paired with vigilance, ethics, and societal oversight. The calm, meticulous approach of the original scientists provides a blueprint. Precision, reflection, and collaboration can harness immense power while mitigating harm. Ultimately, the Manhattan Project's influence on civilian nuclear energy embodies a profound paradox. The same knowledge that once enabled instantaneous, unprecedented destruction now fuels cities, powers research, and saves lives. The serene work in laboratories and secret cities, once focused on war, evolved into a foundation for sustainable, controlled, and innovative applications of atomic energy. Humanity learned that curiosity and careful observation, when paired with responsibility and ethical consideration, could transform a source of terror into a source of progress, illuminating both the possibilities and the profound obligations of scientific discovery. Section 11. Nuclear Diplomacy, Treaties, Ethics, and Global Responsibility. As the world emerged from the immediate shock of Hiroshima and Nagasaki. The Manhattan Project's legacy shifted from the laboratory to the international stage. The unprecedented power of atomic energy demanded not only scientific understanding, but also political foresight and ethical deliberation. Leaders, diplomats, and scientists alike recognized that controlling nuclear technology would be essential for global security, and the quiet, precise work of the Manhattan Project now became the foundation for a complex system of treaties, norms, and shared responsibility. The earliest diplomatic discussions focused on preventing further nuclear catastrophes while preserving national security. The United States, having demonstrated its nuclear capability, sought to establish a strategic advantage, but it also faced pressure to engage with allies and former adversaries in shaping the post-war world. In 1946, the United Nations convened the first international discussions regarding atomic energy and weapons, laying the groundwork for ongoing dialogue about control, inspection, and cooperation. The Manhattan Project had illustrated that knowledge alone was insufficient. Policy, ethics, and diplomacy were now integral to the responsible application of scientific discovery. One of the most significant early attempts at regulation was the Baruch Plan, proposed in 1946 by the United States. The plan called for international control of nuclear energy, including monitoring of production facilities and prohibition of weapons development by individual nations. While the Soviet Union rejected the proposal, citing security concerns, the plan highlighted the need for multilateral frameworks to manage the consequences of the Manhattan Project. It also demonstrated that science and diplomacy were inseparable. The atomic bomb's development had created a technical reality that required equally innovative political solutions. The ensuing decades witnessed a series of landmark treaties and agreements, each reflecting lessons learned from the Manhattan Project. The Treaty on the Non-Proliferation of Nuclear Weapons, NPT, established in 1968, aimed to prevent the spread of nuclear weapons while promoting peaceful uses of nuclear energy. It codified responsibilities for nuclear and non-nuclear states alike, emphasizing transparency, verification, and cooperation. The calm, meticulous observations, record-keeping, and experimental rigor developed during the Manhattan Project provided a model for how verification and monitoring could be conducted, how human knowledge could both empower and safeguard society. Other treaties focused on specific hazards and risks. The Partial Test Ban Treaty of 1963 prohibited atmospheric nuclear tests, reducing radioactive fallout and environmental impact. The Comprehensive Nuclear Test Ban Treaty, signed decades later, aimed to eliminate testing altogether. Each of these agreements was rooted in the understanding that the technological possibilities revealed by the Manhattan Project came with ethical and environmental obligations. The same force that could annihilate cities demanded oversight, caution, and a collective commitment to prevent misuse. Ethics became a central component of global nuclear diplomacy. The Manhattan Project had forced scientists to confront the consequences of their work firsthand, from the laboratory to Hiroshima and Nagasaki. These reflections informed broader debates on human responsibility, scientific morality,
and the delicate balance between knowledge and power. Philosophers, theologians, and ethicists joined policy discussions, emphasizing that the ability to manipulate fundamental forces of nature carries a corresponding duty to consider human welfare, societal stability, and environmental integrity. Scientific advisory committees became integral to the political process, drawing on the calm, methodical approach honed during the Manhattan Project. Experts analyzed potential risks, predicted outcomes, and recommended policy adjustments, ensuring that decisions about nuclear weapons were informed by both technical knowledge and moral consideration. This integration of expertise and diplomacy reflected a profound evolution. The Manhattan Project had demonstrated the power of focused human ingenuity, and subsequent policy frameworks sought to channel that power towards stability and safety rather than chaos. Public engagement also emerged as a key dimension of nuclear responsibility. Citizens worldwide, informed by media coverage and educational initiatives, became participants in debates about disarmament, energy, and security. Peace movements, advocacy campaigns, and scientific outreach emphasized the dual nature of atomic knowledge. It could both illuminate and destroy. The calm, careful experiments of the Manhattan Project thus inspired not only technical innovation, but also a global culture of awareness, discussion, and ethical reflection. The arms control era further highlighted the ongoing tension between innovation and restraint. Initiatives such as Strategic Arms Limitation Talks, SALT, the Intermediate Range Nuclear Forces Treaty, INF, and modern non-proliferation agreements all trace their philosophical and procedural roots to the Manhattan Project. The precise measurements, rigorous documentation, and careful observation that had characterized nuclear weapons development now underpinned verification protocols, inspection standards, and international compliance mechanisms. Humanity had learned that extraordinary capability requires equally extraordinary diligence in monitoring and governance. Ultimately, the legacy of the Manhattan Project in nuclear diplomacy demonstrates a central paradox of human achievement. The capacity to harness unimaginable power brings with it a responsibility for vigilance, ethics, and cooperation. The calm, meticulous work in secret laboratories, once focused on wartime objectives, became the foundation for a global framework in which knowledge, power, and morality are inextricably linked. The world's ability to survive and to flourish depends not solely on scientific mastery, but on the wisdom, reflection, and ethical foresight with which that mastery is applied. In this context, the Manhattan Project was not only a scientific endeavor, but also a profound moral and political turning point. Its quiet laboratories, precise calculations, and tireless experiments ultimately shaped decades of diplomacy, international policy, and ethical debate. By observing, recording, and reflecting on the consequences of their work, the scientists involved helped establish a global principle. The exercise of extraordinary power demands both technical excellence and moral clarity, a lesson as vital today as it was in the dawn of the nuclear age.
Section 12. Beyond the Bomb. The Manhattan Project's Technological Ripple Effects. While the Manhattan Project is most often remembered for its role in creating the first atomic bombs, its influence stretched far beyond weaponry, shaping a wide range of technological innovations that continue to resonate today. The meticulous experimentation, large-scale coordination, and interdisciplinary collaboration that defined the project created a blueprint for scientific advancement, with ripples extending into energy, computing, medicine, space exploration, and even materials science. One of the most significant technological legacies lies in computing. The Manhattan Project demanded calculations of unprecedented complexity, from neutron diffusion and chain reaction modeling to explosive lens design and critical mass estimation. Early electronic and mechanical computing systems were pressed into service to solve these problems, pushing the limits of processing power and algorithmic design. These efforts laid the groundwork for the digital revolution. Innovations in data storage, computational modeling, and problem-solving techniques developed for the project later informed the design of modern computers, numerical simulations, and high-performance computing systems that underpin contemporary science and engineering. In energy, the Manhattan Project's research into nuclear fission opened doors to controlled energy generation. Although initially focused on producing plutonium and enriched uranium, scientists quickly realized that the underlying processes could be harnessed for peaceful purposes. Nuclear reactors, originally prototypes for weapons production, became the foundation of civilian nuclear energy. Lessons learned in reactor design, thermal management, and radiation shielding directly influenced the development of safe and efficient power plants, enabling cities to access a potent source of clean energy. The calm, precise experimentation of Manhattan Project laboratories translated seamlessly into engineering protocols for large-scale, reliable energy production. Materials science also benefited profoundly from the project's innovations. The handling of uranium, plutonium, and other radioactive elements required the development of specialized alloys, corrosion-resistant containers, and advanced fabrication techniques. These breakthroughs influenced industries far beyond nuclear applications, from aerospace to electronics, medicine, and industrial chemistry. The meticulous testing and observation that defined Manhattan Project research ensured that materials could withstand extreme conditions, a principle that continues to guide engineering design across fields. The project's influence extended to medical technology as well. Radioisotopes, produced for research and energy purposes, quickly found applications in diagnostics, treatment, and biological research. Techniques developed to monitor radiation and protect workers informed safety protocols in hospitals and laboratories worldwide. Nuclear medicine, including imaging technologies such as PET and SPECT scans, relies directly on knowledge and methods that trace back to Manhattan Project experimentation. Here, the quiet, careful work of scientists seeking precise control over atomic reactions translated into life-saving applications for millions of people. Space exploration represents another remarkable avenue shaped by the Manhattan Project's legacy. Rocketry, satellite development, and deep space missions benefited from innovations in materials, propulsion knowledge, and computational modeling. The project's integration of physics, engineering, and logistics created a model for coordinating large, complex projects involving multiple disciplines and institutions. Programs such as NASA's Apollo missions drew inspiration from this approach, demonstrating that the same principles which enabled the construction of nuclear weapons could also facilitate exploration beyond Earth with precision, collaboration, and foresight. The Manhattan Project also transformed approaches to large-scale project management, coordinating thousands of personnel across multiple secret sites required innovative logistics, communication, and oversight strategies. These methodologies were adapted in post-war industrial, governmental, and scientific endeavors, large-scale infrastructure projects, research initiatives, and technological programs learned from the Manhattan Project's example, emphasizing interdisciplinary collaboration, meticulous record-keeping, and iterative problem-solving under pressure. The calm, methodical approach of the project became a template for achieving ambitious, high-stakes goals in diverse fields. Ethically, the Manhattan Project's ripple effects prompted profound reflection on the responsibilities accompanying technological power. The same scientific principles that allowed for rapid innovation could yield consequences far beyond the laboratory. Modern scientists, engineers, and policymakers continue to grapple with these lessons as they develop artificial intelligence, biotechnology, and energy systems. The careful experimentation, risk assessment, and moral deliberation emphasized in Manhattan Project labs serve as enduring reminders that innovation must always be coupled with ethical foresight and societal consideration. The project also influenced public perception of technology and science. The sudden visibility of atomic energy, both destructive and generative, inspired awe, curiosity, and caution. Education, media, and literature explored the implications of harnessing such immense power, encouraging the public to consider both the possibilities and responsibilities inherent in scientific advancement. The calm, deliberate work behind the atomic bomb became a symbol of human ingenuity, tempered by reflection, a lesson in humility and vigilance for generations of scientists and citizens alike. Finally, the Manhattan Project's ripple effects extend into research culture itself. The integration of multiple disciplines, the reliance on precise measurement and observation, and the emphasis on collaboration created a new paradigm for scientific work. Today, interdisciplinary teams tackle challenges in climate science, quantum computing, biotechnology, and space exploration using principles first refined in secret Manhattan Project laboratories. The project demonstrated that when knowledge, discipline, and ethical reflection intersect, humanity can achieve extraordinary feats while remaining mindful of the broader consequences. Ultimately, the Manhattan Project's technological legacy embodies a paradoxical but inspiring truth. The same work that enabled unparalleled destruction, also seeded a century of innovation, discovery, and human progress. From clean energy to medicine, computing to space exploration, the calm, precise, demonstrating that when knowledge, discipline, and ethical reflection intersect with precision, collaboration, and iterative problem solving under pressure, and collaborative approach of Manhattan Project scientists continues to illuminate the path forward. Humanity learned that curiosity, rigor, and responsibility are inseparable, and that the power to transform the world carries both promise and profound obligation. Section 13. Reflections and Legacy: The Manhattan Project's Enduring Lessons. As the Manhattan Project recedes into history, its significance remains profound, extending far beyond the technical achievement of splitting the atom. The calm, meticulous work in secret laboratories across the United States created a legacy that shaped science, society, ethics, and the very way humanity thinks about power. Reflecting on this project offers not only historical insight, but also a meditation on responsibility, curiosity, and the capacity for human ingenuity to shape the world in both perilous and extraordinary ways. The Manhattan Project demonstrated that extraordinary challenges could be overcome through collaboration and focus. Scientists, engineers, mathematicians, and technicians from diverse disciplines worked together in unprecedented secrecy, facing extreme technical difficulties and moral uncertainty. The collective effort, coordinating logistics, experiments, and calculations, illuminated a truth that remains relevant today. Progress is often the product of patience, discipline, and quiet dedication, rather than grandiose gestures or sudden inspiration. In many ways, the project was as much about mastering human coordination as it was about mastering the atom. One of the most striking legacies of the Manhattan Project lies in the lessons it imparts about responsibility. The scientists who created the first atomic bombs understood, in varying degrees, the moral weight of their work. Some grappled with guilt, while others sought reassurance in the belief that their efforts were necessary to end a devastating war. The project illuminated the dual nature of scientific knowledge. It can empower civilization, but without ethical reflection, it can also unleash catastrophic consequences. This lesson extends far beyond nuclear physics, serving as a cautionary guide for any field where innovation can dramatically affect lives, ecosystems, or societies. The Manhattan Project also left an enduring mark on education and research culture. Its approach, combining meticulous experimentation, rigorous documentation, and interdisciplinary collaboration, set a standard for big science. Universities and laboratories adopted these methods, creating a model for tackling complex, high-stakes challenges in physics, chemistry, biology, engineering, and computing. Today, initiatives from space exploration to climate modeling continue to draw upon the organizational and methodological innovations pioneered during the project. The calm, methodical mindset cultivated in Los Alamos and Oak Ridge remains a touchstone for scientific rigor and effective collaboration. The project's influence on global politics and diplomacy cannot be overstated. By introducing nuclear weapons into international relations, the Manhattan Project transformed warfare, diplomacy, and strategic planning. It created the context for the Cold War, the nuclear arms race, and ongoing efforts in arms control, non-proliferation, and disarmament. Governments learned that technical achievement alone does not ensure safety or stability. It must be paired with thoughtful policy, negotiation, and ethical oversight. In this way, the Manhattan Project serves as a reminder that human ingenuity is inseparable from human responsibility. Beyond politics and research, the project reshaped culture and public consciousness. Literature, film, philosophy, and art grappled with the paradox of atomic power, a tool capable of both unimaginable destruction and transformative progress. The serene focus of scientists performing exacting calculations contrasts with the violent, immediate consequences of their work, creating a tension that continues to inspire reflection, creativity, and moral inquiry. The calm discipline behind the project's experiments serves as a quiet counterpoint to the dramatic historical events they precipitated, reminding us that measured effort can have outsized consequences in medicine, energy, and technology. The Manhattan Project's ripple effects continue to enrich human life. Radioisotopes for imaging and therapy, nuclear reactors for energy, and innovations in computing and material science all owe a debt to the meticulous experimentation and interdisciplinary problem-solving that the project demanded. The same curiosity and rigor that enabled scientists to unlock the secrets of fission have since fueled exploration of space, deep-sea environments, and the human genome. Humanity learned that the principles of precision, observation, and collaboration can be applied to build rather than destroy, to understand rather than annihilate. Perhaps the most profound lesson of the Manhattan Project is the reminder of duality in human capability. The very same knowledge that allowed atomic bombs to be conceived also gave rise to nuclear medicine, clean energy, and technological innovation. The calm focus, careful experimentation, and collaborative spirit that produced the bomb also illuminate a path for using knowledge ethically and constructively. Humanity discovered that power is inseparable from responsibility, and that foresight, reflection, and ethical deliberation are as vital as technical skill. As we reflect on the Manhattan Project, one sentence captures its essence more vividly than any other. The serene precision of minds working quietly in secret laboratories had unlocked a force capable of shaping the world forever, reminding humanity that knowledge without reflection can both illuminate and destroy. This sentence embodies the paradoxical legacy of the project, the intertwining of immense human achievement with profound moral responsibility. It encapsulates the calm, disciplined effort behind groundbreaking science and the far-reaching consequences that follow, both inspiring and cautionary. Ultimately, the Manhattan Project teaches that science is never isolated from the world it inhabits. Every experiment, calculation, and discovery resonates beyond the laboratory, influencing politics, ethics, culture, and the future of human civilization. The project reminds us that curiosity, intellect, and diligence are gifts, but they are most powerful when guided by reflection, foresight, and an unwavering sense of responsibility. In this way, the Manhattan Project is not only a historical milestone, but also a timeless meditation on human potential, the capacity to both create and safeguard, to innovate and to reflect, and to shape the destiny of our world with care and understanding. The legacy of the Manhattan Project endures, quietly embedded in the institutions, technologies, and ethical frameworks that define modern science and society. It remains a calm yet profound reminder. Human knowledge is extraordinary, but its true value is measured not just in what we can do, but in how thoughtfully, responsibly, and ethically we choose to wield that power.